Okay. I know you guys are awesome at mathematics, okay? Yeah, and you do extremely well. But part of what I want to teach you guys is about these different shapes and ones that are not so easy to always recognize. So I find examples 3 and 4 today we're going to go over a lot more interesting than our other ones. The other ones is very easy to predict the type of behavior they're going to have. With these, it's more difficult. So part of what I'm going to teach you is that when you have a rational expression, you can just take the largest term in the top and divide it by the largest term in the bottom, and that tells you your end behavior. It's going to look like y is equal to 2. We've already talked about that, right? Let me just change it a little bit, and instead of y equals 2x squared, I'm going to have a 2x to the third in the numerator. When I divide that, what do you get? So if you plug in a very large positive number, you're going to get a very large positive number, infinity. If you plug in a very large negative number, you're going to get negative infinity, right? But it will look like 2x. So what does 2x look like? It's a line with a slope of 2. That's what it's going to look like. So maybe you remember last year when we graphed rational functions, that you maybe put down a vertical asymptote, but then instead of a horizontal asymptote, you had like a slant asymptote. So you can always tell what it's going to look like as it heads off to infinity by simply just dividing those two biggest terms. Now, that's not this scenario here, but if you did see one, say on your study guide, that's what you would do, okay? So our horizontal asymptote is y equals 2. Anybody identify our vertical asymptotes? Where is this undefined? 1 and? Good job. I will find the y-intercept by plugging 0 in for x. And when you plug in 0 for x, you get 0 over negative 1, which is 0. Because when you let this limit go to infinity, you get 2 over 1. The x-intercept, do I look where the numerator is equal to 0 or the denominator? Numerator. Where is the numerator equal to 0? At 0. Okay, now in order to find the rest of this information, I should really take some derivatives. Okay, so how do I take the first derivative? What rule do I use? Quotient rule. So I take the derivative of the top, which is times the bottom, x squared minus 1. You guys remember when we used to spend so much time practicing the quotient rule? I mean, you guys are you're really learning a lot. You are. Every once in a while, you got to look back and say, "Wow, we've learned a lot of information." So as I distribute this, I'll get 4x cubed minus 4x cubed, right? So the numerator looks like I just have a negative 4x over x squared minus 1 quantity squared. Don't know what the graph looks like, so we're gonna have to do some number line testing here. What numbers should I put on my number line for critical points? 1 and negative 1. What else? y0. Yep, that's where the top's equal to 0. That's where it's undefined due to the denominator. Now you tell me this. Tell me something interesting about the denominator. It's always positive. Why? Because you're squaring it, so it's always got to be positive, right? So I don't even need to think about the denominator here. I'm just going to think about the numerator. Negative 4x. At negative 2, it will be positive. At negative 1/2, it will be positive. At any positive values, it will then be negative. So here's another classic example where it doesn't switch signs every time. You truly have to test. So let's mark a couple of these things down. It's increasing from negative infinity to negative 1, union with Good. And decreasing from 0 to 1, union with 1 to infinity. I can identify points of local max and local min. Does it have one of those? Why, Kelsey, does it have a local max? Because it changes from positive to negative. Is 0 in the original domain? Yes. Is negative 1 or 1 in the original domain? No. So we could count 0 as a local max. If you plug 0 into the original function, you get 0. We've already figured out. Turns out the local max happens at the XY-intercept or at the origin. Is there a local min? There's none. Okay, looks like it's time for a second derivative. What rule do we have to use for a second derivative? Quotient. Derivative of negative 4x is negative 4. X squared minus 1 quantity squared. So on Friday, I helped out Sarah and a couple other people made with, I think, problem number 11. This is turning out to be very similar to problem number 11 from your assignment, so should give you some help moving forward. Then we minus the original, so plus 4x, times the derivative of the bottom. How do I take the derivative of the bottom? Chain rule. See how smart you guys are? You guys always know what to do. Derivative of u squared is 2u, and then we have 2x. So we get a 4x times x squared minus 1. All over the bottom squared. Now, here's where, yes. Well, yes, I'm sorry, to the fourth, yep. Here's where Ms. Sorensen had a little issue. You decided to multiply these through here, right? And so what's going to be easier is if we don't multiply it through and we get rid of a common factor. What is a common factor that exists? X squared minus 1, right? And so I could take it out of the numerator and then 1 out of the denominator. So that will reduce this to a third power. That will reduce this to a first power, and this will be gone. And so what I end up with now is, people watching me teach. What I end up with now is I have this negative 4x squared, and I have a positive 16x squared for a total of 12x squared. And then a negative 4 times a negative 1 is a positive 4 all over x squared minus 1 quantity cubed. Negative 4x squared, yep, and then a positive 16x squared. Maddie? No, you looked like you had a question you were not asking. How I got the numerator? All right. Caleb? Doob? No, this does not factor to an x squared minus 1. So, nope. Good try, but no luck. Are you convinced? Okay. So, tell me something interesting about the numerator. If you factor out a 4, it still doesn't really change the problem at all. But you tell me it's always positive. Why is the numerator always positive? Yeah, you square it and then you add 4. It's always going to be positive, right? So this thing is never going to be equal to 0. It's always going to be positive. So I don't really need to worry about the numerator at all. I could just focus on the denominator. And the denominator has the key points of negative 1 and positive 1. And I want to be able to look at x squared minus 1 quantity cubed. So I'm going to plug in negative 2. And I get a positive cubed is positive. Yep. Well, the critical points, I must consider where the top is equal to 0, and it's never equal to 0, because it's always positive. And I have to consider where the bottom is equal to 0. That's where the function's undefined. So that's why I choose negative 1 and positive 1. But right now, I'm only plugging numbers back into the bottom to save time. because I know the top is going to come out to be positive. If you square something and add 4, it's going to be positive, no doubt. If I plug in 0, I get a negative 1 cubed is negative. And if I plug in a positive 2, I'm going to get a positive. So now we know our intervals of concavity. Concavity is going to consist of concave down from -1 to +1, concave up from -infinity to -1, union with my 1 to infinity. Now, you might be tempted to say that you have inflection points. Why do I not have points of inflection? Although I change sign at -1 and +1, I don't have, they aren't part of my original domain. So I don't have inflection points. The original domain is all real numbers except x can't be equal to -1 of 1. Now it's time to graph it, the most exciting part of the day. So vertical asymptotes, I'm going to put those on here. So I'm drawing these. I think we know that we're not going to get a huge snowstorm this week, but we also know that it will get extremely cold this week. So we are going to get down to single digits during the evening. So time to make sure that you're allowing extra time in the morning to scrape that windshield or whatever you need to do, folks. So yeah, make sure you got gas in the car. Okay, I have only 1 point on this graph that I know. What's the coordinate that I know? 0, 0. And I'm going to focus on this interval between -1 and +1. Between -1 and +1, it's concave down. It increases the first half, and it decreases the second half. So it looks like it's going to look like that. And then I either have to be in the top or the bottom over here. Which one is it going to be? Top, Y. Increasing and concave up. Over on the right side, it's going to be in the top or bottom, because it's decreasing and concave up. Very good. And so I'm going to go to my calculator and type in 2x squared divided by x squared minus 1, which I really like. And I'm going to make my window -6 to 6. And then again, -6 to 6. And I'm going to check out this graph. Oh, check that out. I mean, I don't want to brag, but that's pretty awesome. Green and red for Christmas, yes. Oh, wow. We got 3 weeks left, folks. 3 weeks. But your internal clock says 1 week, right? But I'm just saying, like, internal clock says 1 week because we're 2 weeks early. So if you're feeling like, you know what, we should be coming up soon, that's kind of what the internal clock is saying here. Yeah. So if it's saying, well, it kind of feels like it should be coming up sooner, that's why. But then it will be out 2 weeks earlier. One more example. Very nice. All right. I have to admit, you guys, this last type of problem, part of the reason I want to go over it with you, you're not going to have a problem like this on your test. But because you have 2 work days, you know, tomorrow and the next day, I really, really want you to see something that's, I think this is just a heck of a lot more exciting than what we've already done. Okay? All right? It is. Well, no, it's just, yeah. Yeah, it's, sometimes I see a, sometimes I see a function. It's like, you know, 95% functions I see, I'm like, well, I know exactly what it looks like. But every once in a while, I'm like, I don't know what that looks like. Let's try to figure it out. And you know, I've done this one enough now where I know what it looks like, but it still kind of brings me back to that point. So let's figure it out, okay? All right. Y-intercept. All right. Go get some brain food and we'll come back and do this one. Okay. I'm going to sketch this curve. I'm going to find the y-intercept. What do I plug in for to find the y-intercept? I plug in 0 for x. And if you plug in 0 for x, you get 0 minus the sine of 0. What's the sine of 0? 0. Very good. So 0 minus 0 is 0. Okay? And if the y-intercept is 0, that means it's at the origin, so the x-intercept will be 0 as well. Now, part of what I want you to understand is being this has sine of x in it, it's going to have some type of periodic behavior. It doesn't have any asymptotes, but I am going to determine the end behavior by letting the limit go to infinity for the function. And although this may look like a challenging limit to evaluate, it's really not that bad. I'm going to factor out an x, and I get the limit as x goes to infinity of x times 1 minus sine of 2x over x. Think about what happens. Sine of 2x is always going to stay between what 2 values? 1 and negative 1. The bottom is going to get ridiculously large. So this is going to go to 0. So you have a very large positive number times 1, which will give you very large positive number. So it's going to go to infinity. Whereas if you went to negative infinity, you get a very large negative number. So if we did the same thing, we come out with negative infinity. So part of what I want to do here is I want to just try to understand a little bit of this behavior, you know, that's periodic. So as I look at these intervals, I know it's going to constantly change. I mean, if we looked at concave up and down for a sine function, we'd have an infinite number of intervals to list, right? So hopefully we can figure out what it is for a certain section, and then after that we can, you know, just kind of map that over and over again. So we'll see what we can get. Let's start by taking the first derivative. What is the first derivative? I have to use a chain rule. Derivative of the inside is 2. Derivative of the outside is cosine with the inside left alone. Now, part of what I'm going to do here is I'm going to consider this graph. Do you know how to make that graph? This is negative cosine of 2x, 2 cosine of 2x plus 1, right? So it's going to be shifted up 1 unit. It's going to be shifted up 1 unit. Okay. And the amplitude is 2, so it's going to go all the way up to 3 and down to negative 1, right? What's the period? 2 pi over 2, which will be, or 3.14, right? I divide that in half, I get 1.57. Divide that in half, I get 0.78. Yep, 2.34. Where will the graph start? It will start at negative 1, and we'll head up. Same pattern off to the left as it is to the right, correct? So let's just focus on this section right here. Okay. Let's just focus on the period from 0 to pi. I am wondering where the first derivative is positive. That means where it is above the, so that's going to be from this green dot to this green dot, correct? So that's what I need to find, are those 2 points. I want to find where this is equal to 0, or where 1 minus 2 cosine of 2x is equal to 0. So where is 2 cosine of 2x equal to 1, or cosine of 2x equal to 1/2? In which quadrants is cosine positive? 1 and 4. Let's take out our calculator. No, you will not see one like this on the test. I just want you to kind of, so let's cosine inverse 0.5, and I get 1.05. So 2x is equal to 1.05. But then I also have to subtract 1.05. What is all the way around the circle? 2 pi, which is, as a decimal, 6.28 minus 1.05, and I get 5.23. So I'm going to divide each of those by 2. And I get x is 2.6, and I get x is 0.52. So that spot right there is 0.52, and that spot right there is 2.6. So can somebody tell me, just over that interval from 0 to pi, okay, so we're going to just go from 0 to pi right now, where would it be increasing? 0.52, 2.6. Decreasing from 0 to 0.52, union with 2.6 to, I'll write 3.14. Now, here's what's great, is that, oh, well, let's determine the local max and local min. Local max is where the derivative changes from positive to negative. Does it ever change from positive to negative? At 2.6. Does it change from negative to positive? From what? At where? 0.52. So we'll plug that in. And then I want you to think about inflection here, okay? How would I represent the second derivative of this? What would I do to show a second derivative? Draw the tangent lines. Where would a tangent line here have a slope of 0? At 3. Well, at 3.14, right? And at 1.57 and at 0, right? And so we know that we have inflection points at 0 and at 1.57 and at 3.14. Okay? And so then we can plug those in to generate then our y values. So we didn't even need to take a second derivative here. We could just look at that first derivative graph, which was pretty nice, wasn't it? I'm really happy about it. So, okay. So let's go to our calculator. We're going to tabulate some values here. We're going to punch in x minus sine of 2x. And I'm going to go to my table and generate values of 2.6. And I get 3.5. Type in 0.52, and I get negative 0.34. Plug in 0, and I get 0. Plug in 1.57, and I get 1.57. And plug in 3.14, and I get 3.14. So by looking at my graph and using kind of what Claire talked about drawing those tangent lines, where will I be concave up? Wherever the first derivative is increasing. Where is this first derivative increasing? 0 to 1.57, increasing here. And it'll be decreasing from 1.57, 3.14. And now I've got enough to really kind of start to put some pieces together. And so I'm going to make some tick marks here. I'm going to go 8 by 8. 1, 2, 3. I'm going to plot my x-intercept. And I have a local min of 0.52, negative 0.34. I have inflection at 1.57. Then I have a max at 2.6, 3.5. And then I have another point inflection at 3.14, 3.14. So this is my, and then this is my local min, inflection. Now here's what's cool, is that it looks like it should repeat itself after that, right? So I should be able to take this shape and just kind of tack it onto there. And I should be able to take this shape and just tack it on like that. And I should get kind of, you know, that deal, right? I mean, who knows? Let's see. I mean, I made my window 8 by 8. I guess we're setting negative 6. Well, you know, we'll say it's close enough. We'll see what we get here. Happy birthday, Kelsey. I mean, right? I mean, come on. I mean, is that not a good birthday present right there? I mean, that's that's pretty good. And we've never seen that function before, have we? And look at that representation. Pretty much spot on. You know, Newton could be very satisfied by his work to generate how these curves look. You have to your assignment from Thursday to add just 2 problems. So just add these 2 problems, and that's it. Happy birthday, Kelsey. What's that? This past Friday? Friday coming up? I don't know. Uh-oh. All right, so just add that to Thursday's assignment. That should be it. Yep, I sure will. Like, you just drew the graph by looking at your calculator? So you found like points of, you like looked at and said, okay, I know what the, you do need to show, so on the test, I will ask to see the first derivative and second derivative.